Okay, we are live now. Uh, let's welcome our guest today to join the live session, problem solving sessions, Mr. Shaful Das Vishwas. So, today's topic is trivial way to think Erdos, stature conjecture. So, this is our first episode. Next time, we will be hosting more such episodes frequently, but this is a free live session. Yes, so let's welcome our guest, Shaful Vishwas. Hello, Shaful.
Yeah, Shamrita. Hello.
Yeah. So we already introduced your uh, to our session. So it will be the live session, problem solving session. Yeah, you can start now.
Yeah, I'm sharing this. How to share the screen actually? Actually, I
There
don't
will be
know that.
option, na present option. You see.
Oh, present. Yeah. Share screen now.
Yes.
Don't show this deep second. Yeah, share screen. So it's shared
No, not yet.
now.
No, no, no. Share
Okay,
screen. Click on the share screen. After present,
okay.
click on
Wait.
share
I'm
screen.
open the PPT first. Open the representation. PPT presentation. Okay, let me open the PPT presentation. Yeah, done. Okay, wait. Yes, done. Yeah. So yeah, present. Yeah, share screen. There is the option. Share
Hmm.
screen.
Yeah, sure.
Window. Chrome tab. There are option like window and all. Share. Okay, so it's sharing, right?
Yes, yes.
Okay. So hello everyone. This is Shafaldas Biswas. So today, as you all know, I'm going to discuss Erdos conjecture. It means how to trivially think Erdos conjecture. And so let me check one thing. My camera is off. Okay, camera is off. Okay, all okay. All okay. Yes. Okay. So yeah. So it's how to use. So it's visible right now, Shamrita. Hello.
Yes, it is visible. You can
Yeah.
carry.
Okay,
Yeah,
okay,
carry
okay.
on.
So Erdos conjecture. So trivial way to think Erdos conjecture. So I will cover some preliminaries of before talk, that is divisibility of integers and all that. And so let me start the talk without much delay. So okay, so it's not. I mean, what is happening? Oh, I can't go to the next slide. Present. Okay, wait. Share screen. Window. Okay, share. Okay, so Erdos trivial way to think Erdos conjecture. So I'm going to the next slide. Some basic definitions and notations before talk that I said before that I will introduce you guys everyone before the talk. So what are integers? So answer is 0 plus minus 1 plus minus 2 plus minus 3. Note here plus minus 1 means plus 1 or minus 1. Okay. So small remark, 0 is called neutral integer.
Shuffle, are you there? You are not audible. Hello,
So
hello, hello, Shuffle. You are not audible.
important in this session, what are sets is not important, but somehow I give the preliminaries, what are the basic notations of sets. So, and z equals to 0 plus minus 1 plus minus 2 is the set of integers. This is a set of negative integers, z less than 0.
Hello, Shuffle. You are not audible. Can you please your mic once?
This set, as I have said above, as I said before, sorry.
Shuffle, please check your mic or internet connection. I think your voice is not available. Is not audible. You are. I think some internet issues from the speaker end. Okay.
Hmm. Hmm. Sorry for the glitch, guys. Actually, I'm not this handy with this thing, so I'm not handy with this thing. So wait.
Okay, okay, no issue.
I'm not handy with this thing. That's the problem, and I am doing for the first time in this screen. So share screen window, yeah, share. So yes, so come back to divisibility from where it gets stopped. and my network connection is not stable, so it's happening. So yes, so what is divisibility? So a num okay, so a number a b both integers, we say a divides b, written as a divides b. This is the notation. If there exists an integer c, oh, obviously a not equals to 0 because division by 0 is illegal. How, why and how? Don't ask me the question because it's a very huge topic. And there exists a integer c such that b equals to ca. Okay. So example, 4 divide minus 12, as minus 12 equals to minus 3 into 4, then 4 minus 12 minus 3 are integers. Thus, we say 4 divides minus 12, and minus 3 is called quotient here, and the remainder is 0. So is 5 divide 6? No, because if we let 6 equals to 5, see, there is no integer c which satisfy this equation. Okay. So 5 cannot divide c because if c cannot be integer. Now, what are remainders for integers for this lecture? Because remainders are minimum remainders, minimum absolute remainders. There are many concepts. So for this lecture, I will be restricting to the following definition. Answer is, as we have seen before, 5 divides 6 is not possible, but 4 divides 12 is possible. So we have two cases here. For any two integers a, b, case 1, a divides b, we say b equals to case 1, a divides b. That means according to the divisibility notation, a divides b. We say b equals to ca plus r, where c is the quotient, c is said to be the quotient, and r equals to 0, the neuter integer, that is the remainder. Now, why? Because the a divides b, so r should be 0, right? Because we if r is non-zero, then we have this following case that a does not divide b. So in that case too, we should we mean a does not divide b in this notation. A does not divide b. This is the notation of a does not divide b. Then there exists an integer. Then there exists integer q, quotient, and remainder r, which is an integer such that b equals to aq plus r. And what is aq plus r and what r satisfying? Where ba you already know because a does not divide b, and q is the quotient, and what is r? R is greater than 0 and mod a minus 1. What is mod a? Mod a is the positive value of a. That means here you see in example 1 it is minus 12. But when we are taking minus 12, then mod of minus 12 is 12. Mod of also 12 is 12. Okay. So mod takes positive. If a is any integer, then mod transfers that integer to positive value of that integer. That means the distance. Okay. From distance from 0 to some a is called any number a, but we are restricting here to integers. Okay. So I hope this is clear up to this point. And example for case 1, that means a divides b, 3 divides 6, then 6 equals to 2 into 3 plus 0. And q equals to 2 is quotient and r equals to 0 is remainder. As we see that in case 1, r should be 0, is the neutral integer. Example for case 2, 5 divides 4. Now this is an important thing. See, 4 is less than 5. Right? That means 5 is greater than 4. Then how we should interpret the remainder? Then 0 into 5 plus 1. Then, oh, okay. So there is a typo here. Then I write 1 equals to 0. It shouldn't be 1 equals to 0. It should be q equals to 0. That means the quotient is 0 and r equals to 4. That is the remainder. In short form, I write remain dot. This is the notation for remainder. Okay. Now come to the point of 2, example 2 from case 1, case 2, 37 divide 46. Now what is this? Now how to, this does not, 37 divide 46. This is not a proper notation. 37 does not divide 46, but what is, in what sense 37 divide 46? The sense is that 46 equals to 1 into 37 plus 9. Okay, that means if you add, if there is a quotient q equals to 1, so here is also a typo, it should be q equals to 1. So then q equals to 1 is the quotient and r greater than 0 less than 9, which is less than mod 37 minus 1. As you see the definition of remainder here, this is mod a minus 1. So r less than 37 minus 1, which is 36. So 9 is the remainder. I hope it is clear. So, and there is a typo. Firstly, the q equals to 37. I wrote this should be q equals to 1. because 37 divides b, then q quotient should be 1, as because of the definition you can see. And this is the definition we will restrict for this lecture, because there are many concepts like minimum remainder and minimum absolute remainder. There are many concepts, but we will restrict this for this lecture. Fine. Now let me go to the next slide. Okay. Now, what is the definition of a divisor? It should be important, because what is a divisor? If a is an integer, then an integer d not equals to 0, this shouldn't be 0. I didn't wrote, every time I miss that 0. Previously I also missed that 0 there. So if an integer d not equals to 0 such that d divides a, then it has remainder 0. Okay, sorry. Then it has remainder 0, because of the divisibility definition, d divides a when the remainder is 0. So then the d is called the divisor of a. That means if some integer d divides a, then it's called, and left remainder 0, that means after dividing by a you get 0, then it's called divisor of a. Then d is called divisor of a. D can be positive or negative also, but we will restrict that to positive for this lecture anyway. So 1 divides a for any integer a, because a equals to 1 into a. Okay, 1 a equals to 1 into a. That means if you multiply 1 with a, we get a, so we get an integer c, that is a itself. So 1 is the divisor for every integer a. And definition of prime number, prime numbers, as we all know, but still I want to recall, a positive prime number p. Positive, this is an important thing, but prime is anyway positive, so just restrict that to positive, because many people define minus p. So yes, so a positive number p is prime if it has only two divisors, namely 1 and p. That means the only divisor in the previous definition d is 1 or p. We know that 1 always divides p, but p also divides p. Okay, because p equals to p into 1. Okay, so in p has only two divisors. For example, if you take 4 have actually how many divisors? 3 divisors, 1, 2 and 1, 2 and 4. So this is not prime. 4 is not prime. 4 is composite anyway, but 4 is not prime. Okay, so I'm going a little fast, because time, I can't complete it in time if I don't go fast. So sorry for that. I will try to get slow from now. So fundamental theorem of arithmetic, I will go without proof, because the proof is too long to cover this in good time. So every integer greater than 1 can be written as the product of prime powers. What is prime powers? That means if you raise a prime number to the power some alpha, alpha greater than equals to 1, and alpha is an integer, then p to the power alpha is called prime power. Okay, I didn't typed it here, but it's okay. So yeah, so we will not go through this proof, but the rough idea is it uses strong induction. So primes are building blocks of numbers. So because of this fundamental theorem of arithmetic, people often say primes are building blocks of numbers. Fine. So we know 2 equals to 2. That's obvious. No? So we are excluding 1 in prime. 1 is not a prime. Please note. Because by if you know tau function, then you will actually realize why tau function, that is the counting the number of divisor function, then you will realize why we need to restrict 1 as a prime. So example, 2 equals to 2, which is obvious. 9 equals to 3 square, so 3 is prime, as I said, prime power, so 3 square is a prime power, so 9 equals to 3 square. 18, so you can see how we write 18 as a multiplication and or the product of prime power. So 2 into 3 square, and 36 actually 2 square into 3 square, so these are all prime powers. So 96 actually 2 to the power 5 into 3. Okay, so see how prime power, so every integer can be written as a product of prime powers. For example, 120, you see here, it's 2 cube into 3 into 5. 2, 3 are all primes. Note, these 3 can be prime or cannot be prime. That doesn't make the prime power. Prime power means 2 to the power alpha. Prime power means p to the power alpha, where p is prime and alpha is an integer greater than equals to 1. Fine. The alpha may be prime, may not be prime. So that's a thing. And 5040, this is actually 2 to the power 4. See here, 4 is not prime, so 2 to the power 4. So but it's a prime power. Obviously 2 to the power 4 is a prime power. So 2 to the power 4 into 3 square into 5 into 7. Fine. So all are primes and all are prime powers, you can see. So this is the basic definition of prime powers, and this is it. And so I hope you all get up to this point what are the definitions, because it will be important, and crucially prime powers theme is important. Okay, so go to the next slide. So introducing the hero of the show. So the main hero of the show, the main attraction of the show, Erdos conjecture. So what is the equation of Erdős conjecture? As you see, 4 by n, 4 over n is equals to 1 over x plus 1 over y plus 1 over z. So this is the equation, and the main equation you will also see in the next slide. Now this is the equation, but there are restriction to x, y, z and n. So here is the question for Erdős conjecture. Does the equation 4 by n equals to 1 over x plus 1 over y plus 1 over z has positive integer solution x, y, z for every n greater than equals to 2? So this is the Erdős conjecture. Till yet, I hope you get this point. Okay. So the main question is, it is not known whether this is true for every n. That means we can, for every n there exist integers x, y, z positive such that this equation holds. Okay, fine. Now, so not known, but the amazing fact is there are infinitely many integers for which this is true. We will come to that point soon. Infinitely means there are many integers, many sequence of integers for which this is true. That means n can take infinitely many values for which it holds that 4 by n equals to 1 by x. But is it true for every integer? That is the question, and that is the crux of a Erdős conjecture. Okay. Now, as you have seen, I have written the search is for every integer n greater than equals to 2, not a finite subset of positive integers. That means it must we want for every integer, not for a finite subset of positive integers. Okay, so soon we will see that every integer n greater than equals to 2, say j. That means I am saying that integer j. Okay, saying that integer j that was divisible by 3. That is j equals to 3k for some positive integer k, and every integer that left remainder 2 upon dividing by 3, that is j equals to 3k plus 1, works for n. As I said, there are infinitely many integers. So n equals to 3k and n equals to 3k plus 2 works for n. For every n of this form, that means 3k and 3k plus 2. That means that the integers that left remainder 2 upon dividing by 3 and the integers that left remainder 0 upon dividing by 3 works for n. Okay, so now 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 hence our search is for every integer greater than equals to 2 for 3k plus 1. That means the integers that left remainder 1 divisible by 3. If you prove this fact, that I will be showing the proof of the 3k plus 2 and 3k form, but if anyone can show that j equals to 3k plus 1 also works for some for every integer k, then you are done. That means you are solving the conjecture. Okay, so I am not going to solve the conjecture because it's still a conjecture and it's very hard to show why 3k plus 1 should work. But yes, if you show j equals to 3k plus 1, you will definitely get famous, and it will be like a groundbreaking result, because it's a conjecture for j equals to 3k plus 1 where k is a positive integer. Now, how we can ensure that if n greater than equals to 2, we only check for integers of the form 3k where k greater than equals to 1. Why only 3k? That is the question. Why only 3k and 3k plus 1 and 3k plus 2? Is there other integers? This is because here is the crux, that this is because every positive integer upon dividing by 3 can have firstly two choices. First choice, 3 divides the number, that is the remainder 0. or we say or we say it is of the form 3k. That means when a number is divisible by 3, we say it is 3k. If it does not divide 3, then the remainder is actually between, if 3 does not divide that integer, then the remainder is between 3 and 2, as we know from the definition of remainder as I already give. So thus, now r is an integer and r is between 0 and 2. What are the possible choice of r? What are the possible integers between 0 and 2? Between 0 and 2, including 2, but not including 0. That is 1 or 2, right? Okay. Because there is no other choice. Because 1 or 2 is bigger than 2, but r is less than 2. So r can be at most 2. And r can be 1 also, because 1 is greater than 0 and less than 2. So only possible choice of remainder r is 1 and 2. Thus, for each case, if an integer gives a remainder 1, then we write that the integer is 3k plus 1. Okay. So here is the matter that if the remainder, if a integer 3, if the integer is divisible by 3 and leave remainder as 1, the integer is actually of the form 3k plus 1. And if it gives the remainder 2, then it's when we write 3k plus 2 for k greater than equals to 2. Thus we have three forms of integers, if you have already noted: 3k, 3k plus 1, or 3k plus 2. Now if you if you think cleverly, you can see that if we subtract if we subtract from the state of natural number the set 1, then you can see that 3k such that k1 2 3 dot 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 so on, integers, union 3k plus 1 k1 2 3 and so on, union 3k plus 2 k0. We need to include 0 because unless we cannot cover the 0 in this integer set. If you see that here it start from 3, here it start from 4, but we need to include 2 because n greater than equals to 2 in our question. So 0 1 2 3, and if you see, these two sets are actually equal. That means we can partition the set of integers, including 1, if you also take set of positive integers in 3k, 3k plus 1 and 3k plus 2, where k is an integer positive. So every integer can be written in this form: 3k, 3k plus 1 and 3k plus 2. And if we subtract that 1, then we need to restrict from, if we subtract, we need to restrict from 1 2 3, 1 2 3 and 0 1 2 3. Unless if you allow 0 in this set, 3k k0 1 2 3, then if you allow 0 here, then it's not true. So in this case must start from 1. Okay, what's up? Okay, this case must start from 1, and if you allow 0 here, if you allow 0 here, and if you also allow 0 here, so it is already 0, then n is actually then n is also actually partitioned into, then n is actually partitioned into 3 cosets. These are called, okay, so integer set, I need to define cosets. So okay, okay, don't get into that. So n minus 1 is 3k, 3k plus 1 and 3k plus 2. Fine. This ensures that we cover every integer just by looking at the positive integers of the form. This ensures the why 3k and 3k plus 1 and 3k plus 2, because if we are looking at positive integers, then it must be of the form, as we this condition implies it must be of the form 3k, k greater than equals to 1, 3k plus 1, k greater than equals to 1, or 3k plus 2, k greater than equals to 0, as you see here, and where k is an integer. Fine. Fine. So this is the matter, and this is why we should seek for only of the integers of the form 3k, 3k plus 1 and 3k plus 2. Fine. Now here is the only result and the final result, and I keep the talk short because I have some work after 9 p.m. So I need to keep the talk short also. So here is the theorem. Here is the key claim for their infinitely many solution and the integers of the form 3k and 3k plus 2. So the equation 4 by n equals to 1 over x plus 1 over y plus 1 over z has positive integer solutions in x, y, z if n is divisible by 3. Sorry, I wrote a typo here. So n is divisible by 3, or it is divisible by integer of the form 3k plus 2. Now you might be worried, why divisible by integer of the form 3k plus 2? You will see soon. Okay, now why not integers of the form 3k plus 2 only? Actually, if it is divisible by 3k plus 2, then we can write it integer like 3k plus 2 into 1. So it's true for also 3k plus 2 in integer of the form 3k plus 2. So proof, before proof, I will go to a small anatomy. So what is the small anatomy? That means we need to do some operations on that equation. Fine. So if for some integer n equals to t greater than equals to 2 works, I am claiming that some integer n greater than equals to 2 works. Okay, this is my claim. If some integer works, okay, then if this is my claim. If this integer works, then obviously there exists integer x equals to some xt, y equals to some yt, and z equals to some zt, such that 4 by t equals to 1 over xt plus 1 over yt plus 1 over zt. Now t works, therefore the claim is that t works. If t works, therefore these integers exist, because t works by our assumption. So and these are positive integers, obviously, because the problem is for positive integers. So if then we claim that n equals to rt is also work. That means if you multiply an integer r with t, that will also works. That means if the equation works for t, the equation works for any multiple of t. That means any integer divisible by t, it will also works. Divisible by t and left remainder 0, it will also work. So why it's so? Why is so? So if you let x rt equals to rxt and y rt equals to ryt and z rt equals to rzy, all positive integer, this works. I am claiming this works. This system works. If the previous system works, then the next system of r equals to rt is works for this integers. Why? Because suppose you have this integer t that works. So 4 by t is actually 1 by xt plus 1 by yt plus 1 by zt, as above we said it works. Then multiply both sides by 1 by r. So what we have? We have 4 by rt equals to 1 by rxt equals to 1 by ryt equals to r by rzy. Now these are working for every r, every positive integer r. Okay, because we are assuming 4 by t works. So what is rt? So rt, now we have this following. So t xt, so this, now we know rxt is actually xrt, x base rt, and y indexed rt is ryt, and z index rt is rzt. Fine. Now this notation, that means t xt ryt and zt goes to rt xrt, x base rt, and y base rt, and z base rt. So if this works, then definitely this works. That means we have proven with that anatomy that if this 1 by 4 t works, then that this means if t works, then rt works for any integer t, where t is a positive, where r is a positive integer. We need to restrict that because r should be a positive integer. Now what we can ensure from this anatomy, think. I am giving you an exercise to think that this is one of the first takeaway from this talk, this exercise. That means the below state, if we prove the statement, that means 4 by n equals to 1 by x plus 1 by y plus 1 by z, that is the Erdős equation. If we prove the statement for prime numbers only, that means prime numbers n, then we are done. So why we are done? Because of this small anatomy. Okay. So because of this small anatomy, if we only prove for n equals to prime, then we are done. But primes are many, right? So now if we prove for primes of the form 3k plus 2, this is not enough. We need also to prove for primes of the form 3k plus 1. And that is the crux of the matter. It's hard to prove for the primes of the form 3k plus 1. 3k plus 2, we will see in a second that 3k plus 2 is very easy to see. Okay. So the finally proof of the theorem, and this is we are near to the end of the talk, so no worries, I am fast today. So what is the proof of the theorem? We denote n xyz if it is a solution of the equation of the theorem. That means like before, this tuple I will denote So please note that equation, this equation in your mind, because in the next slide you will not see this equation very clearly. I mean, in terms of n you will not see. So okay. Oh, as I said, in terms of n you will not see. So we denote n x y z if it is the solution of the equation of the theorem. We claim that now note 3 2 comma 2 comma 2, as 4 by 3 is actually 1 by 2 plus 1 by 3 plus 1 by, that means 1 plus 1 by 3. 4 by 3 is actually 1 by 2 plus 1 by 3 plus 1 by 1 by 2 plus 1 by 2 plus 1 by 3. Fine, because this 4 by 3 can be represented in this form. Thus, by anatomy, what we have done before, so you can see that n equals to 3, then we have 2, 3, and 3. So n equals to 3, we have 2, 3, and 3. So n equals to 3. For n equals to 3, we are done. But we need to find all integers, right? But by anatomy, we have 3, 2, 2, 3 goes to 3r, 2r, 2r, and 3r. Right. Thus, every multiple of 3 is covered in the equation. See, 4 by 3r equals to 1 by 2r plus 1 by 2r plus 1 by 3r. We are just multiplying by 1 by r. So every multiple of 3 is covered, because we can take r any integer greater than equals to 1. Okay, so every multiple of 3 is covered, and multiple of 3 works also. So multiple of 3 works where r greater than equals to 1. And this is what I have written. Okay, so I need to zoom it. So wait. Okay, it's 100%. Okay, so 3 works for n equals to now. As I said, I will not prove the theorem for 3m plus 1, because 3m plus 1 is the only hard part and it will solve the problem. But we need for only the theorem I am saying is for 3m plus 2 and 3k plus 2 and 3k. So let's see for 3k plus 2. So for n equals to 3m plus 2, if we have integer for m greater than equals to 0, just note n, if we have 4 by n, then n works for x, n plus 1 by 3 works for y, and n into n plus 1 by 3 works for x, z. So if we have the integer n, then x equals to n, and y equals to n plus 1 by 3, and z equals to n into n plus 1 by 3 works. Okay, since n equals to 3m plus 2 form. Now you say n plus 1 by 3. How you are saying that n plus 1 by 3 is an integer? How you are claiming that this is an integer? Because this should be an integer in the equation. See, this is the matter that, so since n equals to 3m plus 2, then n plus 1 is a 3m plus 3, because we are adding 1. So if we factor the 3 out, we have n plus 1 equals to 3 into m plus 1, where m is an integer. Now divide by 3. So what we have, n plus 1 by 3, which is actually m plus 1. Now m is an integer, because here in this assumption n is of the 3m plus 2, where m is an integer. So n plus 1 by 3 is actually m plus 1. And so n plus 1 by 3 is an integer, right? That means n plus 1 by 3 is an integer. I hope you get that. Why it is an integer? Because n is the form 3m plus 2. Thus, n plus 1 by 3 is an integer, and thus the n, comma n, that means n is the 4 by n, that n, and x equals to n, and y equals to n plus 1 by 3, and z equals to n into n plus 1 by 3. Now you see that n into n plus 1 by 3 is also an integer. Why? Because n plus 3 is an integer and n is an integer, and product of two integers is an integer. Now we are also working on positive integers, so note on that is the working tuple for n, where n is a 3m plus 2 integer. Thus, this is the working tuple for every integer n of the form 3m plus 2. Not only primes, but every integer. Thus, we can restrict it to prime also. That means when 3m plus 2 is prime, right? Thus, by anatomy, if we take a prime p of the form 3k plus 2, as I said, if it, because it's true for every integer of the form 3k plus 2, that is a prime that leaves remainder 1 when leaves remainder 1. Then let eta is the solution, because this solution exists, we know, because of this form. Because of this solution, we know that if n plus 1 is prime, then we always get a solution like this, because it's true for 3m plus 2 integer, as we already proved. Then xp, yp, zp exist. Then we just by anatomy scale this with, multiply all this with s, and we get this equation, and this works. And thus what we have, if you have seen it properly, for example, what I said, for example, if you take a number n that is divisible by a prime of the form 3k plus 2, but that number is of the form 3k plus 1, then that number also works. Now you say, now you see that I told you that 3k plus 1 will not work, but 3k plus 0 plus 1 will work, but we don't know the solution. Then how you are claiming that if p divides 3k plus 1, then it works? Okay, so it's I am claiming this because p is of the form 3k plus 2. And if p divides that integer 3k plus 1, then we just apply the anatomy. Since p divides that 3k plus 1 integer, as I said, then ps is actually some 3k plus 1 integer. Now it's worked for p, so we don't need to worry about s. So we just multiply by s and we get the 3k plus 1 integer. And this will work. And this then does the theorem follow. Okay. So going to the next slide. Okay. Okay. So in conclusion from theorem, so every integer greater than or equals to 2 of the form 3k works, because as we proved that if as we prove what we proved, that if 4 by 3 works, so n equals to 3 works, then by anatomy we just multiply by r, and so 3r works for every integer of the form 3k, right? So every integer of the form 3k works. Now every integer greater than or equals to 2 of the form 3k plus 2 works, because as we shown that n plus 1 by 3 and n into n plus 1 by 3 is the solution for n equals to 3n plus 2. Okay, so every integer of the form 3k plus 2 works. Okay, so now every integer of the form. Now here is the important thing. Now this is the important thing what I'm trying to tell you guys after the proof, that this is the very important thing, that every integer greater than or equals to 2 of the form 3k plus 1, that is divisible by at least one prime of the form, at least one prime, at least one prime of the form 3k plus 2 works. For example, what is some integer of the form 3k plus 2? For example, just take what I said, what I can say, 3k plus 2. Okay, okay. So 3k plus, for example, 25. Okay, 25 is of the form, 25 is of the form 3k plus 1, because 3 into 4 plus 1 is 25. Then how you are claiming that 25 works? I am claiming that 25 works because 5 is of the form 3k plus 2. Like 5 is of the form 3k plus 2, right? Because 3 into 1 plus 2 is 5. So 5 is of the form 3k plus 2. So actually 5 also works. Why 5 works? Just go to this equation, but just plug in terms of 5. So you get 5 comma 5 comma 5 plus 1 is 6 by 3, 2 and 10. So 5 5 to 10 is working for 5, right? Now just multiply that 5. Now multiply both side by 1 by 5. Then we have 5 into 5, 25, comma 25. That means xp is now 25, then 10, then 50. That works for 25. So you see how we transfer the problem into just the primes that are divisible by 3k plus 2. That means the prime when that means any integer of the form 3k plus 1, that is divisible by at least one prime of the form 3k plus 2. Then by the anatomy we are done. We are not done for all integers of the form 3k plus 2, but a large subset of integers of the form 3k plus 2 that are divisible by 3k plus 1. And thus in the end of the talk, conclusion from the talk, basics of integers, remainders, and fundamental theorem of arithmetic. Sorry, actually, I'm firstly sorry because I'm too fast, but I need to cover a lot of the things, and I have some work from 9:10, so I need to cover it before 9. So it's 20:45 now. That means 8:45 now in Indian IST time. So basics of integers, we covered basics of integers, remainders, and fundamental theorem of arithmetic without proof. So this I covered without proof. And I suggest you guys to and there is no book actually what from that means I am going to the before slides. So from here you can't find it any book. This was not in any book. From here you cannot find these things in any book, but the previous things like what I said, like basics of integers, remainders, and fundamental theorem of arithmetic. You will get this in any standard number theory book, and go and read it, and you will understand this talk and review this talk again. You will understand it much better. So thank you, and so thank you, everyone. So, uh, so any questions? So you can ask. So yeah, thank you, Shamrita. Thank you, Cosmic Jared. So yeah. So any
Yeah,
question,
please.
anyone? Yes,
Yeah,
Samrita.
thank you, Saful. Thank you,
Yes.
Saful, for this
Actually,
wonderful
sorry.
session.
Actually, I'm a little fast today because
Mm.
I have a work at 9:10. I forget that to tell you, and the session is on 15 September. So I'm sorry for that.
Yeah, yeah, no issue, no issue. So yeah,
Okay.
if you have any questions, you can just write down in the chat section,
Okay.
YouTube
I
chat
mean,
section.
15 minutes. I'm here. So
Yeah.
please, can you, Samrita? Hello.
Yes, yes.
Shomrita, can you? I don't know where they typed the question, but wherever they did, can you tell me the question by unmuting yourself? Because it will be better.
Yes, yes. I will show you in the YouTube screen. You can see from there.
Okay,
I
okay,
will
okay, okay, okay.
pop.
So I'm stop sharing
So,
right now. I
yes,
can
yes. You
stop
can
share,
stop
right?
sharing. Yes,
Okay,
yes.
okay. Thank
Yeah. So yes, people who have questions, please feel free to ask in the chat box.
you. I think there is no questions yet.
There is no question. Yes, yeah. So I would request everyone to please ask questions.
I am fast, so you can ask any question. So I'll be happy you just ask questions.
Yes, yes,
So I'm
yes.
sorry, I'm fast actually. So please ask questions. I'm there for another 10 minutes, so you can ask.
Yep.
You can go to the previous video, and I mean, this is live, so you can go to the previous minutes by scrolling the that part, and see where you find any doubt or something, and ask me.
Yes, yes, yes. Exactly.
So no questions yet.
No questions yet. So
Okay, 10 minutes I'm waiting, so no problem. Another 5 minutes I'm waiting, so no problem.
yeah, yeah, sure.
Actually, I'm too fast today. That's the problem. So I don't know how much I make them understand. But I had actually I'm too fast. I'm sorry for that. So
Yeah, no problem. It is our pastime.
because I
So
need to
yeah,
cover all these things within 1 hour. So I think that 15 minutes for questions and before and up till 1 hour, up till 45 minutes I will go for the session. So that's why
yeah,
I'm
yeah.
fast also, and also I have a work from 9:10, some work. So that's why I'm fast today. So
Yes, yes, yes. Definitely, definitely.
but I hope so. If anyone wants the PDF, so I will send the PDF to them. So
Yeah, you
please,
can share in our group also.
yeah, I will share in the group. But I don't know how many of this YouTube in this YouTube live session they are in the group. So let them introduce to the group also. I
Yes, yes,
mean,
definitely.
yes, let them introduce the group also. So if anyone wants the PDFs, you can actually contact Shomrita, or you can comment in any of the posts of Cosmic Chat that you want to join the group, and there we will get the PDF and ask for the PDF. And I will already upload the PDF after 10 p.m. today. No worries. I will give it to
Yeah.
provide it to Shomrita.
Okay.
And okay, so and if so what is S? Indrajit, what is S? What is YJM? I don't know. Can you speak out?
No, no, no. There is no option to speak out. You have to tell in the comments box only.
What is YJM? Can you WJM?
I
Sorry. What
think
is
this is
WJM, Indrajit? Can you?
mistype. No, no, no. Ignore. This is mistype, I think.
Oh, acha, mistype. Okay, 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 okay. No problem, no problem, Indrajit. So another 4 minutes. I'm here. So can ask questions. So I will upload the PDF. It will be initially tough to actually grasp Erdos conjecture, I must say, because it's not that easy thing. But once you actually introduced to the concept of remainders, and I had tried my best to actually introduce to the fundamental theorem of arithmetic to you guys, to everyone. But I, for example, prime powers. So why it's actually prime powers? So you can actually see that I mean, if you try small cases, I mean, when the fundamental theorem of arithmetic was actually made, it was obviously trying small cases, right? And trying small cases, you actually generalize it. So obviously if you just trying to generalize the concept of fundamental theorem of arithmetic, you just need to try small cases and see how you actually inductively proceed. So sometimes it's not only using small cases, because sometimes small cases not always help, but most of the time it helps. And that is the thing. So fundamental theorem of arithmetic, if you just try using small cases and see how to use that smaller numbers to actually jump to the bigger numbers. Okay. And this uses this principle of strong induction. Now, many of you don't know strong induction. Even many of you know induction, and only few of you know what is strong induction. Strong induction is called second principle of induction. Okay. So I will not go into what is strong induction. Strong induction says if you prove the problem for some integer, if you want to prove the problem for n plus 1, just show the problem for 1 to some s where s lesser than equals to n. We know that induction for n, right? So if it's true for n and n plus 1, then it's true for n plus 1. Now in strong induction, you just need to show that for s lesser than equals to n with some conditions, and then trying to prove for n plus 1 using that s for s lesser than equals to n. Not only n, now we can use s also. That is the principle of strong induction. So that is the way to prove fundamental theorem of arithmetic. But it can be used in many ways. I mean, strong induction has many applications, and most of the Olympiad problem that uses inductions is actually based on strong induction. Okay. Okay,
Okay, I
so
think, yeah, I think we can wrap up now because no
okay,
one is
so
there
yeah,
in the
sayonara to
live.
everyone and bye bye. So thank you, Shamridha. Also,
Yeah,
thank you,
thank
Obhirup.
you.
Yeah, so bye. I can leave the chat, right?
Yes, yes, I am ending the
Okay,
streaming.
okay, okay, okay. Thank you.